everyone. Thank you for coming. Today is my great pleasure to introduce Professor John Kleinberg, who is the Tisch University Professor in the Department of Computer Science and Information Science at Cornell University. John's research focuses on interaction of algorithms and networks, and in particular, the role they play in large-scale social and information system, and what are the implications for societal impact. And I have to say, of course, John's research is very foundational, had profound implication for network science, and has been recognized by many different awards. So he's a member of both the National Academy of Science and the National Academy of Engineering, and is the recipient of the MacArthur, Packard, Simon Sloan, and Vannevar Bush Research Fellowship, as well as numerous prizes and awards, including the Harvey Prize, the Nevalina Prize, and the ACM Prize in Computing. And so today is going to talk about aligning AI with human behavior. So we are very much looking forward to hear about your talk. Thank you so much.
Okay, well, thanks. Yeah, thanks very much for the invitation, and it's great to be able to be part of this seminar series. And yeah, so and definitely if there's if questions come up, happy to sort of take questions, especially if there's something that I can help clarify. And similarly, if there's any obviously sort of issues with the connection or anything, happy to sort of stop and troubleshoot that. So this is a talk that about some work that I've been doing with a number of colleagues over the past few years in a sort of mainly in an applied direction, trying to think about model systems in which AI has sort of long since surpassed the best human performance, and to actually just try thinking about, in this applied sense, what we can actually learn from some of these domains, and what that might tell us about other domains where transitions like that have not yet happened or seem sort of further out in the future. And so this is joint work with a number of colleagues. We sort of began this, Ashton Anderson, Senthil Mullainathan, and me, roughly in 2015, thinking about the way in which chess might be a useful model system for thinking about this. And then more recently, a sort of long-running project with Ashton, his student Reid McElroy-Young, Sid Sen at Microsoft Research, and Russell Wang, who is moved from Toronto to Berkeley. And in particular, thinking about some of the actual tools that we could potentially build around this. Okay, having said all that, so what was the idea? So the starting premise was really to try studying a creative pursuit in which algorithms have conclusively surpassed human abilities. And the idea was, that as often when we think about the sort of far future of AI, there's almost no choice but to descend into the realm of speculation, right? What might mathematics look like once algorithms and AI are just better at it than humans? What will music look like if we got to a point where algorithms are composing the music that we listen to? What does post-human journalism look like? What does post-human all those kind of questions, right? So and the problem is these are inherently speculative because they seem to refer to some counterfactual in the future that we don't really know how to talk about. We don't really know what it'll look like. And so the question that we asked ourselves was, could we study this instead by looking at a domain where this has already happened? Now, there are obviously some domains where this has already happened that we don't think of as good analogies for, for mathematics or art or music or writing or things like this. So for example, obviously algorithms have transformed, the practice of sort of, numerical accounting. Like if we have to keep track of things, spreadsheets are very good at that, but we don't, in the present, that in fact was obviously a very disruptive change, but in the present, we often don't think about sort of that particular kind of transformation the way we would about some of these on the horizon. And so the sort of desiderata that we wrote down for the kind of domain that we'd like to study is, again, sort of these 3 points at the bottom of the slide. We wanted to find an area where you get these incredibly high levels of human achievement, as you get in art and music and sports and so forth, where you sort of sense that there's a sense of mastery that's been achieved, right? Where people train their whole lives to reach this level. That's on the sort of one person's lifetime. On the kind of societal level, we wanted a domain, again, like music or mathematics, where it's the subject of, a century more of accumulated prior work. And finally, it's something where algorithms have somehow just conclusively surpassed humans, in some sense that's really not even disputable. And so the domain, as the title of the talk suggests, that we arrived at, which does have all these properties, is chess, right? And chess, of course, is a model system that many people have used in the past. So many of the sort of names that we associate with the foundations of computer science, information theory, artificial intelligence, economic theory, all at some point thought about chess. So in these photos we have Claude Shannon in the upper right presenting an award to one of the creators of Deep Blue, Fengsheng Xu, and then we have Alan Newell and Herb Simon in the upper left. Alan Turing worked on chess. Von Neumann worked on chess. So its value as a model system has been sort of long present, and for obvious reasons. And this obviously in the bottom is the sort of famous 1997 match between Garry Kasparov, the world chess champion at the time, and Deep Blue. It's viewed as a model system for sort of a natural reason, which is it's a completely self-contained system. One doesn't require knowledge of the rest of the world to understand what's going on the chessboard, yet it presents humans with sort of puzzles that seem to be sort of right at the limit of their understanding, right? Not too hard for us to sort of contemplate solving, but hard enough that it's a sort of endless source of rich challenges. Now, in this domain, right, and again, obviously the best chess players in the world, practice their entire lives. They reach this high level of mastery. There's a scholarly literature on chess that certainly rivals the literatures of many academic disciplines as well. It's also, and so for that reason, its role as a model system has been sort of captured metaphorically in a number of ways, right? So Simon and Chase described it as the Drosophila of psychology, in the sense that the Drosophila, the fruit fly, is the sort of model organism for genetics, and chess was being used in their research as a kind of model organism for psychology. Similarly, John McCarthy, one of the pioneers of AI, called it the Drosophila of artificial intelligence. But now there is this new thing going on, which is that they're really making those statements, in a way, at a moment when the idea of chess, computer chess surpassing humans, was aspirational and sort of uncertain. Now it's long since conclusive. And so now the computers have far since surpassed the best human chess players. There's sort of three kinds of questions that we want to ask, and I'll break the talk into sort of three short parts that each cover one of these categories of questions. One is the question of, now that computers are sort of beyond humans, can we actually go back and use it as a lens on human behavior, right? In sort of, one of the other benefits of chess is it can be recorded precisely. And so, in online forums where people play chess, you have literally hundreds of millions or billions of recorded chess games, each of which represents somebody's decision-making. Can we do things like characterize human error in these kinds of situations? What positions tend to lead to, predictable errors? Part two, if we can do all of this, can we actually design algorithms to simulate human behavior, right? So in some sense, the standard goal for computer chess is to win chess games. But what if the goal were something else? What if we instead turn the lens on human behavior and said the goal of computer chess is to try as accurately as possible predicting what humans will do in a given situation? What kind of tools would we arrive at then? And finally, it's interesting to ask about almost the cultural question. If we're going to ask what disruptive influences chess might computers and AI might have on mathematics or music or journalism or law or any of these things, we could look at the ecosystem of professional chess and ask what actually happened when machine superintelligence actually arrived in this domain. Okay, so first let's start by getting sort of more concrete. That lays out the plans that we had. No particular knowledge of chess is going to be assumed in this talk, other than chess is a game in which you get continuously presented with cognitively challenging puzzles, and it's a zero-sum game in which the outcome is either a win, loss, or draw for the players. But so let's talk about computer chess. So all through the 1990s, computers got steadily better and better. And there was sort of this question that at some point, everyone began to accept that there was nothing magical about human abilities in chess. Computers were eventually going to beat the best human beings. Depending exactly what you declare as the ground rules for beating the best human beings, that happened on a few dates, right? So the sort of highest level of human performance, the sort of human grandmaster category, right? The first recorded win under tournament conditions in the late 1980s. Garry Kasparov, the then human world champion, right? In some sense, the sort of Mount Everest of this was defeat the human world champion in a match under normal conditions, and that happened in 1997 with IBM's Deep Blue computer. And then, of course, the public's attention sort of moved on to other things the challenge had seemed accomplished. And so, in some sense, to public perception, people sort of missed what was, in a sense, the actual more dramatic continued evolution in which computers just kept getting better and better and better, right? It wasn't like some asymptote was reached as far as we could tell. So, first of all, it moved from the supercomputer that Deep Blue ran on onto desktop computers in 2002, 2003. The last recorded win by a human player against a computer engine running on a standard desktop was 2005. By 2007, computers could do things that, strong chess players do to weak chess players, like they, offer that, they'll start with one fewer pawn or one fewer knight or something, and they can still win the game. And at some point beyond there, the mindset shifted, sort of beyond 2007. The sort of best human chess players in the world stopped thinking of computers as opponents and just started thinking of them as like tools that they would use to research chess positions, to train, to practice. But there was no longer a notion that you're going to compete against this as an actual opponent. It's just simply too good. Okay. The other thing that will be sort of useful for concreteness is the sort of rating system for chess. And it's always been an interesting feature of chess that there's a one-dimensional rating system that actually captures skill relatively well, as in everyone has a numerical rating, and if two players of different ratings sit down to play, the one with the higher rating tends to win fairly consistently, with a probability determined by the difference between them. So this is a domain in which sort of a one-dimensional heuristic for sort of level of chess ability has tended to work pretty well. And just to get oriented on those numbers, if you're a sort of amateur chess player who plays it as a hobby, most ratings for people like that are sort of in the 1,000 to 1,800 range. An 1,800 rated player is reasonably good. If you sort of work really hard at chess and you're extremely good at it, you see ratings like 2,300, 2,400, and then there are about 100 players in the world above 2,700. The best 2 or 3 players are rated 2,800, and at this point, current chess engines are well above 3,300 in rating. And again, it's the absolute difference in ratings that determines the win probability. So chess engines are as better than the best human players as they are, relative to relatively, good amateur players. Okay, so chess as decision making. I've sort of, covered this ground here, right? We're going to think of chess as providing a sequence of cognitively difficult tasks. And when a player makes a move, what's the information we have? So we have information about the instance itself. This is the chess position they were facing. We have information about the ELO rating of the player. We also often have, information about the time that they had available to make the decision or the time they spent making the decision. And the question is, for this first part of the talk, could we retrospectively look at a lot of this data and try to sort of characterize the mistakes that people are making? Or in the language of chess, human blunders, which is sort of the chess term for, a sort of unambiguously bad move. Right, okay, so a typical instance of our question looks like this frame from a YouTube video by 2 of the best chess players in the world. On the right is Magnus Carlsen, who many think is the best player, best human being ever to have played chess. On the left is Peter Svidler, who's a sort of one of the top 10 players in the world, right? So Magnus Carlsen from Norway, Peter Svidler from Russia. This is a tournament where they're playing speed chess. And as you see, Peter Svidler's hand is hovering over the chessboard. He is about to grab a piece and move it somewhere. And we could ask, is he making a good or a bad decision when he does this? So how should we do that? So one way to do that would be to use chess engines themselves to evaluate moves, right? And this is a kind of approach that people like Ken Regan have advocated, for example. So you plug this position into some super powerful chess engine like Stockfish, which you can run on your laptop. You can download it. It's extremely powerful. And it will express its opinions about what move they should make. And it's doing some kind of game tree search, which involves a heuristic score for the quality of the position after each possible move. And so you see here that it thinks that if Peter Svidler moves rook to c4, and again, the chess specifics aren't crucial for us, then it's going to evaluate the position at minus 1.41. If he moves rook to c2, it's minus 1.07, and so forth. And the notation here, which won't be crucial for us in most of the talk, is that sort of each +1 is sort of the equivalent of one side being 1 pawn ahead, but otherwise in a sort of positionally equal situation. And so minus 1.4 is like, and minus refers to black doing better, plus refers to white doing better. So this means that this would give black the biggest advantage, and they would have some non-trivial advantage. And if you now, well, what's the problem with doing this? The problem with doing this is if I run the YouTube video a few frames forward, you see that Peter Svidler grabs this pawn and pushes it to g4, which is the computer's third choice. And so you could ask, is that a mistake? Well, Stockfish thinks it's sort of a mistake, but it's not really a binary decision. It's sort of it's a continuum. And the problem is if we go all the way back to, in the end, chess is a zero-sum game, you could ask, does moving the pawn to g4 instead of the rook to c4 actually change the outcome of the game? It's unclear, right? The game might in fact be a draw with best play under the best move. It might also be a draw with best play under the third best move. Clearly, Stockfish happens to like the first move better, but at some point, this is a question of, is this a matter of taste or a matter of actual quality of the position? What is the quality of the position if all we really have is a win-loss draw outcome? I'll come back to some of those questions, but it does suggest that maybe what we should do is go to actually the minimax value of the chess game. And we can actually do that, provided we make the positions simple enough. So if I run this YouTube video a couple minutes further forward, then it turns out Peter Svidler doesn't handle his advantage in the chess position very well. I mean, they're playing very, very quickly, and Magnus Carlsen is the best player in the world. And they get down to a new position. And this is the frame from the YouTube video. And if you look closely, you see there are now 5 pieces on the board. And this is another rendition of it. Now, so what we could do is look at this part of the game, because we could use the fact that chess has actually just been solved for pieces for positions with most 7 pieces on the board, using not chess engines, which do game tree search, but these things called table bases, which are just astronomically large lookup tables that literally have every position. I mean, there are only some finite number of configurations of how to put 7 pieces on a chessboard. You can just write them all down. And actually, in one of Richard Bellman's original papers on dynamic programming in the 1950s, one of his original applications of dynamic programming was to create chess table bases. Because he's like, well, start with all those things which are either checkmate, stalemate, or bare kings on the board, and then just start working backwards. What's everything that's 1 move away from those positions? What's everything that's 2 moves away from those positions? And you just keep working backwards until you've filled out the entire lookup table by dynamic programming. And table bases are really kind of amazing objects, because the point is these positions are actually hard for the world's best players. Like this position, we discovered that there are 18 legal moves. 9 of them lead to forced wins under optimal play at various levels, numbers of moves required, and 9 of them lead to draws with best play. And if you actually advance this YouTube video yet a few more seconds forward, you see that Magnus, whose move it is, has his hand poised. He's reaching out to grab the rook. He grabs the rook and he moves it to the square g2. And we go into the table base and we look up rook to g2, it's a draw. As in, Magnus had 9 ways to continue winning this position, but he threw away the win and played a move that actually forced a draw. Okay, so in other words, he blundered in this position. And of course, the funny thing is, like, at least with the chess engine, you can see the thing kind of struggling and straining to find a good move. Table bases are sort of weird, right? Because for table bases, all positions are equally easy or hard. You show it a position, it just looks up the answer. It doesn't think of positions as easy or hard. It's just a big lookup table. And as a result, much got written in the early 90s when people began constructing these things, right? The idea that, like, in the same, it almost felt like, when Paul Erdős used to talk about, proofs from the book in mathematics, right? He had this whole metaphor that, when a mathematician died and went to heaven, they could sort of see, this book that God maintained of the best proof for every theorem found presumably by brute force search. And that somehow the book was sort of almost this magical thing incomprehensible to humans. And when table bases began appearing, people are like, now for chess endgames, we have the book, because we actually have literally the best way of playing every position. There was something sort of strange and magical about it, and also profoundly incomprehensible to people. But we could use it now to say, is someone blundering in this position? And we don't have to rely on the taste of Stockfish or some other chess engine. We just look it up. So we did this. And we used data from 3 sources, and we've since done this with a number of other sources. And so one is to take about 1 million games played by the strongest chess players in the world. This is our grandmaster data. We took 200 million games from the free internet chess server, and this is people, amateurs, rated between about 1,000 and 1,800, which again covers a pretty wide range of skills. And then you can go to other sites like Lichess, which is the largest free site on the internet, which has over 1 billion games that people have played. And we took all instances with at most 6 pieces, and we just asked, does this change the min-max value of the game? And if so, classify it as a blunder. And then we asked, can we start to characterize features of chess endgames that make them more prone to blunders? Like, what is hard about a position? This position is brutally hard in that the best player in the world messed it up. What is hard about these positions? So presumably skill affects your probability of making a blunder. So let's just do a first plot on this data. The plots here tend to be very smooth because we have an enormous amount of data. And so here's this very simple thing you can do. On the x-axis is the ELO rating of the player. And players are bucketed by their ELO rating. So we take all positions encountered by somebody of a given ELO rating. And on the right is the empirical blunder rate, which is of all positions faced by people of that ELO rating, on what fraction did they reduce the minimax value using their move, right? Change a win to a draw or loss, change a draw to a loss. And what you see is sort of, and you would sort of hope as step one that the plots that the curve should go down, and the curve goes down. Players rated 1,000, basically 1 in every 10 positions they encounter in an endgame, they're actually reducing the minimax value, which incidentally you can only do when you're not already losing, because when you're losing, you can't reduce it further. It's impossible to blunder when you're in a lost position under this definition. And we should come back to that point, obviously, but under this definition, obviously, it's impossible to blunder by definition. And then the very good players, once there's a difference between 2,300 and 2,700, and you're down to almost a 1% error rate at that point. Okay, so what are some features of the position? And part of the talk here is going to be a sort of struggle to find reasonable descriptors of positions. And you'll see in the talk, we don't necessarily get very far into this activity. It seems challenging, but part of the hope here is to just sort of lay out in front of you a whole set of questions that we wrestle with. I think a lot of them are sort of suggestive of questions you might ask in other domains, right? You could ask this question, what are the analogs of this question when we think about humans trying to prove theorems, or humans trying to drive cars, or humans engaged in almost any activity that we think of as sort of requiring some creative insight. So one simple measure that would apply in chess and would apply in actually many domains that we can write down very, very concretely for 6-piece endgames would be a simple measure of difficulty that we'll call the blunder potential, which is if you were to choose a random decision in this situation, what is the probability that it would be a blunder? And so, for example, in this position that we had from our YouTube video, there are 18 legal moves, 9 of them preserve the minimax value and 9 reduce it to a draw. And so the blunder potential is simply 0.5. Now, you can create heat maps here and say, like, as a function of the number of legal moves and the function of the number of plausible blunders, namely the numerator and denominator of this ratio, what is the actual empirical blunder rate? And one thing you find is that as the blunder potential goes up, the blunder rate goes up monotonically with it, which on the one hand there's some obvious intuition behind that. On the other hand, I guess that was not actually what we guessed before we built this plot. And the reason we didn't guess that is because sort of there's an intuitive reason we didn't guess it and almost a complexity theoretic reason we didn't guess it. The complexity theoretic reason is that we sort of know that in general, the hardest instances of a problem are not the ones with a unique solution, right? If I tell you I have a problem and it has a unique solution, often that implies it has some structural, sort of hooks that you can grab onto that actually make it slightly easier. And just from pure intuition, if I'm playing a chess game and there's a unique way I can avoid losing, it seems maybe more likely I might find it because maybe it's obvious. Maybe it's, I should, recapture, the queens have just been exchanged. All I have to do is recapture. That's the obvious only way to not lose. But that's not true when you aggregate over everything, right? In aggregate, all of those things, might be true, but they're lower order effects than just the fact that availability of blunders makes them more likely. Okay. So that's a characteristic of a position. Could we use this, say, to just build a simple predictor of whether a player is going to blunder? So what could we do here? So we could say, let's take the some basic features of the instance, right? Again, this is an instance of the problem, and we'd like to predict, is the player who's about to move, white in this case, going to make a blunder? So we could use as simple features the ELO rating of the player, the ELO rating of the opponent. We could use the time that's remaining in the game, like how long do they have available, and then we could use this number that we had, the blunder potential, which is again a one-dimensional number. Right, so that's sort of 4 simple numbers. We want to have a very simple classification problem. We could then do a bunch of other things. Later on in the talk, we're going to sort of just explode the number of features because we're going to start turning to using sort of really powerful machine learning models. We're going to say like what would happen if we actually took a neural net and looked at the actual chess position, but that's a bit downstream of the talk. So far, we're just asking this very simple question: are any of these features all on their own, reasonably predictive? And of course, we could do other simple features that record, say, blunder potentials deeper in the tree, right? It would be natural to think that, like, if it's harder for my opponent to find the winning move after my blunder, I might have a hard time recognizing that it's a blunder. Okay, and so, but if I take these top 4 features, one thing that's sort of interesting is that actually, if I just use simple decision tree algorithms, then with these kinds of features, I can get about 75% accuracy on a balanced data set of figuring out if there's going to be a blunder, of which the blunder potential is doing almost all the work. Like as a one-dimensional feature, if I simply threshold on blunder potential, I can actually get 73% accuracy in predicting blunders. And these other things like ELO rating, time remaining, things like this, they're very, very small effects. So what's funny is that to the decision tree, just using these simple features, if I say, we're sort of in a, imagine that we're, let's just take the sort of 2 most salient ones here, the blunder potential and the ELO rating of the player. And I say, imagine that I'm sort of in the sort of skill difficulty plane, right? There's 2 dimensions here. One is the difficulty of the instance, that's blunder potential, and one is the skill of the player, that's the ELO rating. Then to the prediction algorithm, one of those dimensions has almost all of the information in it, right? It's almost entirely about the difficulty of the position, and somehow the skill of the player doesn't seem to matter, which is a little strange, a little counterintuitive, because you have to, you sort of ask yourself, but don't we often talk about, what makes someone great at chess and what goes into being a great chess player? We focus so much on that, and we often don't ask as much like what makes a position hard, what makes a position difficult or challenging. And yet this is somehow saying that for prediction, for this very simple prediction task using very few features, the blunder potential is much more informative than the rating of the player. And you go back and you ask, can we actually see that in the data? And the answer is actually, you do see an echo of that in the data. And let me show you where that shows up. So let's go back to this kind of plot. In this kind of plot, again, I have this was an aggregate plot, which just said over all positions, here's the rating. I'm going to bin all positions by people with this rating, and I'm going to look at their empirical blunder potential. But what if I just stratified these curves by the blunder potential? So rounded to the nearest 10th, what is the blunder potential of the position? And then look at all positions of blunder potential 0.1, 0.2, 0.3, and so forth, and ask, what are the empirical blunder rates for those as a function of rating? So rather than one curve here, you're going to see sort of 10 parallel curves, one curve for each bucket of positions that all have about the same blunder potential. And if we do that, we get the following thing. And it has this sort of non-crossing ladder-like shape, which is what the behavior of the prediction algorithm sort of should have led us to suspect, which is these are the positions of blunder potential 0.9. They are very difficult. You blunder at a high rate here. These are 0.8. These are 0.7. And there's a certain non-crossing nature to these curves. It basically says, a player of rate 1800 is just much, much better than the player of rating 1200. If the 2 of them sit down to play, the player of rating 1800 will win almost every time, right? Essentially, once you have a 400-point rating difference, that's kind of the sort of rule of thumb for when the better player is going to almost always win. And yet, if you were to ask who makes more blunders, oh yeah, so a good question, right? It's conditioned on reaching a position with a small number of pieces. Yeah, so does that diminish the importance of player ratings? Empirically, that is not the case. If you were look at game outcomes conditioned on few piece endgames, you still get roughly, the rating differential still has a lot of predictive values to the outcome of the game. But yeah, it's a good question. Right, and these positions are actually quite frequent. In the online chess, or roughly 10% of the games reach a position like this. So a very large fraction of the games on these, or certainly a very non-trivial fraction of the games on these things, like sort of the order of 10%, are decided by the player's performance in these kinds of things. So these are not sort of esoteric situations that come up. They come up very frequently. Right, it says that the right, blunder potential and ELO. Yeah, so a fascinating question is like, do players with higher ELO rating tend to find themselves in a position of higher or lower blunder potential? There's less of an effect than you might think. And we actually went looking for a number of these things. For example, maybe part of your strength as a player is to put your opponent in positions of higher blunder potential. And you certainly see that, sort of case by case. If you look, you certainly see strong players seeking out positions where they can create difficult challenges for their opponent. On the other hand, in aggregate, in this data, it's hard to pick up on those effects. So they don't seem to be the high order effect. But you definitely get this effect where, right, the player of 1800 is actually blundering at a higher rate when the blunder potential is 0.8 than the 1200 player when it's 0.7. And of 1800 at 0.7 is blundering at a higher rate than when this is 0.5, right? So it really is the staircase where the 600-point rating difference is producing less variation, again, in this aggregate view, than the 0.1 difference in blunder potential. And I mean, it's really quite extreme, right? The 2700, there are 100 players in the world who rate 2700 or higher, but they're blundering at rate 0.06 when the blunder potential is 0.9, whereas the 1200 rated player is blundering at about rate 0.03 when the blunder potential is 0.2, right? And so, so this hardness scale, it says that there's an incredibly steep gradient to the hardness of the position. This is actually a phenomenon that you see in other analysis of, say, competitive events. So this is sometimes termed, the fact that instance by instance, you actually see less difference than you think between players of very different skills, sometimes called the Abelson paradox, named after a paper by Abelson in 1985, which looked at Major League Baseball, and that very good baseball players on a pitch by pitch basis are often sort of hard to tell apart. Even the batting average is a composite of their behavior over multiple pitches, and so there's something similar going on potentially here. Okay, now we actually have these questions about but different kinds of players get into different kinds of positions, and there's a huge amount of aggregation going on, and that's certainly true. So one thing we could actually try doing is, in fact, fixing the exact position, right? So with 200 million games, each with roughly 40 moves by each player, right? So we have several billion moves at our disposal. We can actually stratify things all the way down to the individual position. So for these few piece positions, there are several thousand of them that occur 100 or more times. And so we could take those and fix the exact position. Okay, and so we could say for position P, we could say let F sub P of R be the blunder rate of players of rating R in position P. And so again, it's exactly like these curves, right? Or even this curve, right? So we're going to have a curve like this, but we're going to have a curve like this literally for every position that occurs at least, say, 100 times, or enough times that we can get a reasonable curve out of it. Okay, so this curve is now going to be parameterized by position. And obviously this curve went down. That was our basic sanity check, because as you get better, you make fewer blunders. So we could ask that as a predicate of a position. We could say a position is skill monotone if F sub P of R is a decreasing function of R, that players of higher rating make fewer blunders in this position. And obviously the natural conjecture we went in with actually was sufficiently a conjecture. It was sufficiently intuitive to us that we didn't even think of it as an explicit conjecture, was that all positions should be skill monotone. And that turned out to be actually false in the data. So here are 3 examples of positions. And in fact, what you see is that there exist positions where higher rated players, there's an ELO rating not shown on the x-axis here, but this again runs from 1200 to 1800. There are positions where the stronger players are more likely to blunder. Now, I should say a couple of things about these positions, because we did a bunch of sanity checking of this. Was a little surprising to us. First of all, these are positions of, in order to get enough frequency, these tend to be 3-piece positions, and many of the most commonly occurring ones are king and pawn versus king. And king and pawn versus king positions don't have that many pathologies associated with them. As in, if you have the king and the pawn and you're playing against the player with the king, there's essentially an algorithm for winning if you can, right? Some of those are won, some of those are drawn. None of them are losses, right? Once your opponent has only a king, you cannot lose. So you're really trying to figure out, can you win or draw, right? There's essentially an algorithm you're executing that wins if you can win. And the question is, how good are you at executing the algorithm in all situations under conditions of very fast time control and where your opponent is doing unpredictable stuff, right? And so this is not a case where maybe the strong player is deliberately reducing the min-max value because they're having some long-term plan. Like, this is king and pawn versus king, and if the player can successfully preserve the min-max value, they're going to preserve it. But somehow, in certain of these king and pawn versus king positions, they're doing a bad job of this. Also, these positions differ a lot in their blunder potential. So we were curious, like, can we learn anything qualitatively from what's going on? And again, as I said, this is sort of a talk that's in the whose goal is to really just put out lots of questions that we discovered, where we have a lot of hypotheses, but we don't have a lot of really concrete exact answers, because we're getting at things that are mechanistically quite complicated, like why are better players making mistakes in these situations. But just as a sense of like, how much these positions differ in their difficulty, here's a scatter plot of all positions on free internet chess server that occurred at least 100 times. X-axis for each dot is the number of occurrences. Y-axis is the blunder potential. And you see that positions with kings and pawns can actually differ by a factor of close to 10,000 in their blunder potential, right? So in this position with black to move, essentially, everyone as black knows that you should tuck the king in the corner and then the pawn won't promote. Whereas this position was encountered 140 times on the free internet chess server with black to move, and only once did the player find the correct move, actually. In every single other time they threw away the minimum exit. Right, so this almost is a kind of automated way of discovering interesting chess puzzles, because you simply brute forced your way over the entire free internet chess server and you find the positions that people encountered 100 or more times and essentially never found the right answer to. And actually, if you start looking at some of these, and so, in our team, the best chess player was Ashton. And so we were sort of relying on him. And we also were relying on a number of sort of, grandmasters whom we interacted with over the course of this research, and sort of were asking them. And so you end up with some interesting questions about, why are certain things happening? So for example, this position, let me spend one slide on this. And again, knowledge of chess isn't required here. But this is actually the position of all the king and pawn versus king positions that occur at least 100 times. This is the one with the highest empirical blunder potential. This is the sense in which this one is the more people make the most mistakes. And there's something actually interesting about this position, which you sort of don't need to know chess to see, which is that obviously, you can sort of translate a given configuration of pieces around the chessboard. So I could take this hard position, I can move it anywhere I want around the chessboard, keeping the kind of the two kings and the pawn in similar configuration. And the blunder potential goes way down as I move it around. And why is that? It's because actually there's a misleading analogy going on. In this position with black to move, black will preserve the draw if they drop their king straight back, but if they go back diagonally under the pawn, they actually lose. But everywhere else I translate it, what you should do is the opposite. You should actually drop the king back under the pawn. If you drop straight back, you lose. Right, and so there's sort of a natural hypothesis for why this position is so difficult. It's because you have to actually do the opposite of what you would do when you see this shape everywhere else on the board, right? And so one thing that we've been pursuing is to actually say, like, can we formalize this notion of like there's an analogy here, and somehow we're trying to we're violating the analogy when we do that. The actual skill anomalous position has not actually tended to yield much insight. It's sort of a question of like, right, this is the position, where better players don't do the right thing. There's a kind of misleading analogy problem going on where, there are a lot of situations where you shouldn't push the king ahead. Here you should, but it's been hard to find conjectures. It's quite robust. This position occurs a lot. And as you know, chess is left-right symmetric and black-white symmetric. So there are 4 echoes of this position, right? I could reflect the board and I could reflect the colors. And in all 4 of them, it is skill anomalous that the stronger players make. So there is a certain robustness to what's going on, but we don't fully understand it. There are a lot of other things. I want to move on to more complex feature representations, but there are many interesting questions that you can reflect on here, which are admittedly at a sort of a very high level. One is just the kind of thing about how different a scatter plot like this is from the traditional way you would teach somebody chess endgames, right? You traditionally teach chess endgames out of a textbook. You say, here's a taxonomy of all knowledge, and here we're going to teach you the basic things. The scatter plot is sort of saying, you should probably spend your energies up here because this is where everyone makes mistakes. These are both frequent and mistake prone. And you probably don't need to spend a lot of time down here because trust me, when you encounter this position, you'll probably do the right thing. Everybody does, right? And so there's this interesting notion of like, even just the kind of use of data like this to suggest people, where should I spend my effort is almost an interesting sort of thing to think about. And there are other things that, the instant we think about sort of AI for, non-monotone to the time remaining. Yeah, we did actually do a control for time remaining. And I mean, one thing is these positions, so this is speed chess, and these positions tend to get reached near the end of the game. So these are people moving under almost sort of reflex conditions, right? They're moving very, very fast. And so actually most of the data comes when there's relatively little time left. And when we bin just down to that, we still see the same effects. But yeah, it is an interesting question what's going on. And we certainly can't rule out there's something weirdly artifactual happening, although it's becoming increasingly hard to find what that might be. There's also these interesting things that the aesthetics of chess endgames, right? There's this endless debate: is chess a sort of sport, art, or science, right? It's competitive like a sport. It's a science in that people actually do research and try to find sort of improvements in what they're doing, and it's an art in that people admire the elegance of certain positions. And certain positions are obviously, famous. There are these famous chess studies where the solution is viewed as sort of beautiful in the same way that mathematical proof is viewed as beautiful. And again, it's sort of striking that each of these is literally a single line in the table base, which just grinds out the answer, and it's equally difficult or hard. But there is something actually a little subtle, because the table base is not actually trying to find what's elegant about these answers, which is the table base is simply saying, how long, so in this position on the right, this famous endgame study from 1895, from the table base's point of view, the objective function is that black is just trying to drag the game out as long as physically possible. But that doesn't actually convey the elegance, in which, often the sort of the variations that make this thing elegant are the ones that humans would intuitively try, which don't actually drag the game out as long as possible. So in some sense, the elegance of a position is not necessarily contained in the table base, which just has this objective function of like the length of time till it wins. So there are sort of a lot of interesting things to think about here. But I want to sort of move from these extremely sparse settings back to just sort of the middle of the game, the sort of complex middle of the game, and go to much more powerful feature representations. And I'll kind of move more quickly through some things that we've been looking at in these situations. So, for example, I've been talking about, can we characterize people in these very skeletal situations where we have table bases, we have the minimax value. Let's go to the middle of the game where we certainly do not have the minimax value. And we can ask, can we learn to match human decisions in just unrestricted play in the middle of the game, right? So given a position P encountered by a human player of ELO rating X, can I just predict the move that the player will make? And so far we've been doing these very simple things, blunder potential is very, but let's actually treat this as an actual machine learning problem. The instance is the position, and the goal is to predict what a human of a given rating will do. Now, if I take a standard chess engine that's just doing alpha beta tree search, like Stockfish, it's very hard to figure out how would I build it's asking a different question of the position. It's saying, in this position, what is the best move to make that maximizes my likelihood of winning the game, not what is a human of rating X likely to do. And it's hard to figure out how to adapt Stockfish to do that. But with the creation now roughly 3 years ago of chess engines based on deep neural nets, beginning with DeepMind's AlphaZero, and now the sort of fully open source version of AlphaZero, which is called Leela, which was built by the open source chess community, it actually becomes possible to think about taking the architecture of one of these things and training and changing the objective function, right? We're now going to evaluate the deep net not on long-range game outcome, but on whether it matched what humans of rating X actually do in that position, right? So we take the, tens of billions of positions encountered on Lichess, stratified by rating, and we train something, based on the architecture of Leela, try predicting what a human will do. And so, again, with Reed, Ashton, Sid, and Russell, we trained this chess engine that we called Maya, built on top of the Leela network architecture, but basically changing the, right? So Leela's doing deep reinforcement learning, and in the limited time, I won't go into all the details, but it basically has these two heads on the neural net, a policy head that chooses a move and a value head that's trying to estimate the probability of a win. And it's doing some kind of explore-exploit to sort of have the policy head end up putting most of the probability mass on moves whose value head gives a high win probability. Maya, on the other hand, is going to have a policy head that's again specifying a move optimized for matching with the human, but the objective function is now to maximize the probability that over the training data that it's actually matching what the human does in these situations. Now, what would it mean to do a good job at this task? Well, it has this parameter X, right? We'd like to be able to tune Maya to be able to essentially play like a human. And so, ideally, we would like a sort of set of curves that look something like this, which is we have, again, ELO on the X-axis. And we have different versions of Maya parameterized by X. And for each version of Maya, so this is Maya 1200, which sits here. And you would like its performance of move matching accuracy is sort of get very high, but also to kind of peak at 1200, right? Because it's tuned for 1200. Maya 1800 might, peak at 1800, and so not only should we have sort of high values, but somehow it's actually sort of tuned, presumably to that value. Okay, so step one is maybe this problem is already solved by existing chess engines. I mean, after all, when, if for those of you who ever play, chess things on your phone, you can set the level. You can say, I'm going to dial this all the way down to level 0 or level 1, where it still beats most people. But essentially, you're limiting the search, right? It's right. So Stockfish comes with heuristics that limit its search depth and sort of try to make it just worse. And so maybe in being worse, it plays, it starts to play like humans. Or, to put it another way, is there sort of only one way to be bad at chess, or is the badness in Stockfish actually very different from the badness in weak human play? And so you can try this with Stockfish, and you actually get curves that look like this. And the answer is that Stockfish is not, limiting the depth of Stockfish is not really a good way to match players of low rating, because in fact, at every depth, Stockfish does better at matching good players than weak players, right? It's just a question of how high it gets and what the slope on the curve is. Right, so it's not actually, by lowering the depth in Stockfish, you're not somehow shifting it more toward players of low rating. You're just making it weaker. And actually, there's an interesting fact that we fully do not understand. I'll just point it out, which says something about chess and how humans play it, and how chess engine and how alpha beta search works, maybe, or minimax game tree search works. But if I look at how well Stockfish does at matching humans at different depths, it's non-monotone. Here it is at depth 1. Then I think you can see my arrow in the screen share, but it starts at 1, fairly high up, down to 3, down to 5, back up to 7, 9, 11, so forth up to 15. As in, it is worst at matching humans at depth, 1, 3, 5, 7. Why are intermediate depths worst at matching humans is obviously a question that lacks any simple answer, because it has something to do with how humans play chess and how minimax game tree search works on chess, but it certainly is not what we're expecting to see. We could do the same thing with Leela. We could limit the amount of search that the Leela neural net does. And now we get curves that are actually, again, surprisingly flat, which we, again, don't fully understand what's going on here. I mean, some of them are actually just completely flat, right? This version of Leela 2700 is equally good at matching all humans of all ratings. Humans of all ratings, as in one of the earlier questions, get into very different kinds of positions, right? So it's not saying that, humans of all ratings, sort of are somehow equally competitive with Leela. That's not what it's saying. But it is saying that something about the distribution of positions that come up is sort of somehow flat from Leela's point of view. And if you look at the y-axis, it is doing better than Stockfish. But when you're actually trained to match human performance, you do much better still. And so this is the performance of Maya, which is Leela, where we change the policy head and the value head and have to make a bunch of other architectural decisions to match humans. And you actually get the kind of string artifact that you were sort of expecting, that Maya tuned to different ratings peaks at different values of ratings. And in an absolute sense is much higher than when you try to get Leela or Stockfish to match things, right? So it exceeds them by sort of, it exceeds the best Stockfish or the best Leela at move matching by sort of 10 to 15% accuracy per move, okay? And the interesting thing is that with a thing like Maya, you can actually sort of, again, do sort of diagnostics on blunders and chess positions, but now sort of in a much, in a much more complex sense, in a way that sometimes it's, sort of hard to interpret than with chess endgames, right? So you can say, for example, just to take one pedagogical example, if you plug this position into Stockfish and ask what's the best move for white, it will say, the pawn on b5 takes a6. What the human in the data actually did was they pushed the pawn to b6, attacking the queen, which actually, if you think about it, is a really bad move, because you're not stopping the queen from taking the pawn. But again, we won't get into chess discussion here. So, but the human did do that. They played this tempting move. And if you run through the Mayas tuned to different levels, you actually see sort of the rating at which Maya concludes that people will stop making this mistake, right? It goes from the move b6 to the move b takes a6, somewhere around rating 1500. And so it becomes a way of diagnosing chess positions and sort of talking about, how do, diagnosing chess positions and sort of saying, which ones are easier and hard, sort of, again, this sort of goal that we had now applied to these sort of much more unrestricted kind of settings. And again, we're sort of a long distance from figuring out what are the ingredients, right? As I said, like the original goal was to really understand something about the ingredients. Blunder potential and sparse endgames seem to be giving us some sense of this, but there are a lot of interesting sort of hypotheses to be made here. And of course, you can also just use Maya in generation mode. So we released Maya onto Lichess as a bot, because Lichess is an ecosystem where sort of humans and bots kind of mingle with each other and they play, and you see, humans playing humans, you see humans playing bots. And it was nice to see that actually people actually found the experience of playing Maya actually quite a human-like experience. It became quite popular in Lichess, and it now is actually the most active player on all of Lichess. It's actually played over a million games. If you go on Lichess, you can challenge Maya 1, Maya 5, Maya 9. So the 1100, 1500, 1900 versions are there. We got this appreciative tweet from Garry Kasparov. But it's been interesting to see sort of some of the things that happen when you actually release the engines and actually watch what happens as humans use them. One actually interesting question that comes up, which becomes a design decision, right? So now that we're somehow in charge of a bot that people enjoy playing, we end up having to make decisions about what makes for sort of an enjoyable playing experience. One interesting question is actually a calibration question, which, those of us who think about sort of, optimization under uncertainty sort of encounter in a lot of domains, and you encounter it with these chess engines, which is Maya 1100, which is the most popular one, produces in every position, it produces a distribution. These are the probabilities of all the different moves according to my model of what an 1100 rated player will make, right? So this one has probably 0.7, this has probably 0.2, this has 0.05, 0.03, and so forth, and there's some tail. If you're actually using it to play, if we're using it to predict and we want to maximize accuracy, we should pick the move that it puts the highest probability mass on. That will minimize our loss function. If you're using it to play chess against people, what should you actually do? And what we do is we actually pick the argmax, right? So it always plays the highest likelihood position, which means it is not rated 1100, because an 1100 rated player is sampling from their distribution and mixing in, the less probable moves with the more probable moves. When you always play the most probable move according to the model, as we do, you end up with something that's not rated 1100, but more like 1400, 1500. Because it's basically like an 1100 player who always, right? So it's an interesting sort of almost, sort of thought experiment of like, what would happen if you took an 1100 rated player who's very noisy in what they do, and they always played the move that they are most likely to play, right? You would actually become much better, right? Much of your sort of, right, and the argument here is that, at least according to this model, you would get 300 to 400 rating points better if you could somehow prune out your low probability moves, which are often the source of much of your trouble. But it also becomes a design choice. And actually one thing that we're sort of working on right now is like, is there a way to do kind of not argmax Maya, but distributional Maya, which actually samples from the empirical distribution? It sort of seems like a nice idea, but it's not as, in pilot studies, it just plays such crazy moves that people find it kind of weird. And so this is an interesting question of like, what is the right parameterization of this distribution to create kind of, the right experience for people? All right, last part of the talk is, and in the last 5 minutes, we were curious about this question also, right? All of this has been about these very powerful chess engines, but this is also happening in the profession of competitive chess, right? There's this ecosystem of professional chess players who are like every other kind of professional athletes. They take part in tournaments, they earn money from it, they practice, they have coaches, they have support teams. And imagine that you took a sport like that and into it you dropped this, massive change, these chess engines, right? In some sense, the singularity happened in professional chess. You went from the, in the 1980s when, two people, Garry Kasparov and Anatoly Karpov would play the world championship, you would have the situation where at the end of the game, the two people who understood what had happened in that game the best were the two players at the board. And you would interview them after to say like, why did this thing happen on move 28? And why did this thing happen on move 34? And it's almost like we're through the looking glass, because we're now in a world of professional chess where at the end of a game between, the two best players in the world, they're the two people who understand least well what just happened in the game, because everyone watching the game was watching it with chess engines turned on, and they know what they should have done, and they know where they made mistakes, and and so the players will emerge, and the whole press conference thing gets turned on its head. They actually ask the spectators, like, where did I go wrong? Where could I have still held the draw? right? Because it's the players with the engines who actually know, it's the spectators with the engines who actually know what's happening. So it's been a massive change. And so you could ask the question, can we detect things that have changed in the ecosystem of professional chess as a result of this? And there's a lot of folk wisdom about what might have happened, right? And actually this quote from a New Yorker profile of Magnus Carlsen may have to sort of sum up the sort of top 3 pieces of conventional wisdom in a very compressed paragraph. That, it's sort of unimaginable that someone like Magnus Carlsen, who basically was a teenager in Norway who liked playing chess engines in his bedroom in a country with essentially very little chess culture, a handful of grandmasters throughout the entire country. How did he become the best in the world when you have countries where, you just grow up playing chess in the schools, you have chess clubs, you have, right, in the 1970s and 80s, actually all the way from the late 40s through the early 90s, the Soviet Union dominated the chess world because it had decided as a sort of national project, it is going to produce people who are extremely good at chess. It was taught throughout the schools. There were these incredibly elaborate coaching systems, and almost all the top players in chess were from the Soviet Union, which is why somehow the Bobby Fischer-Boris Spassky match of 1972 was viewed as such a kind of, a kind of momentous event, because it was just bizarre that a sort of loner from Brooklyn who just had like a handful of friends helping him was going to be able to beat people trained by, by the sort of Soviet school of chess. And it only happened that one time. But now with engines, it's like Magnus Carlsen in his bedroom can practice against 3,600 rated engines and maybe can become the top player in the world. So there's a notion that top players can now come from any country, they can reach the top at a younger age. And somehow also there's a homogenization of style because there's a monoculture. We're all playing the same engines. So we asked ourselves, is any of this actually true? I mean, we have the data on where top players came from and what ages they were. So let's ask the first question, like, was there a massive change in the geographic entropy of the world's top 100 players right around 2005, 2007? So we basically took time and we took all the, actually I think we took top 300 players, and we plotted the, the entropy of the distribution of countries that they came from. And just, we looked, is there any jump in the curve? And actually there is a gigantic jump in the curve, but it's not where you think it is. So here's the gigantic jump in geographic entropy. It went way up. In the year 1992, what happened in 1992? It was the end of the Soviet Union. That's when the geographic entropy of the chess world changed enormously. And actually not just because people now gave their affiliations as the different republics that had formerly made up the Soviet Union, it's that people, just reconfigured. The apparatus to teach people was, was no longer there. But around 2005, 2007, really almost nothing, right? This is the chess singularity, and it's kind of flat. It's no match for the geopolitical event that happened. Similarly, the age distribution of chess players, this is the chess singularity. It was falling all through the 80s and 90s. It didn't do much here. And similarly, the actual positional entropy of the opening moves of chess games among top players, at depth 1, 2, 3, 4, and so forth. Here, there actually is like, it's more or less flat. I mean, you can imagine there's a little dip right around 2005, and then it actually somehow rebounds a little bit. But these are very small effects. So it's interesting to kind of go into the actual just cross-sectional data and ask, like, what is actually changing in the world? So I wanted to wrap up here. It's 1 o'clock. But this has been sort of a multi-part study that, again, we've been doing over the past 5-6 years, trying to take seriously the idea of chess as a model system for other creative pursuits where we worry about or speculate about the effect of AI being introduced into them. Because in chess, AI has been introduced in this just profound, discontinuous kind of way. And we've tried to sort of pick out these sort of 3 genres of questions. One is AI as a lens to analyze human performance and error. 2, AI in a generative sense. Can I sort of, rather than trying to win, can I match human performance? And our experience with releasing the Maya bots and Lichess is actually, this is something people resonate with quite a bit. It can actually create a qualitatively engaging experience for people, or at least one they come back to. And finally, can you actually do this kind of almost historical study of like what actually happens to the actual professional ecosystem in this domain? And again, we find it interesting to think about, can we sort of, does this help sharpen our speculation about what might happen in professional mathematics or other kinds of things as we think about this? There are obviously many directions, a lot of which are sort of amorphous and complicated, right? Like just the error landscape here. We feel like we're tantalizingly close to understanding it better, but it seems very, very challenging. There's an interpretability problem, right? Maya, even though it's simulating human beings, its architecture is equally opaque and uninterpretable. We're not quite sure how it's simulating human beings, even though the observable behavior matches it better. And finally, obviously, these sort of implications for these things as partners, as training mechanisms, as tools for teaching and human improvement. And I think that there are a lot of interesting things to consider here, for which, again, chess may well be a very effective model system. So I'll stop there. Thanks very much, and happy to stay after to take any questions people have.
Perfect. Thank you so much for the fascinating talk. I guess we can now open up to discussion. So if people have a question, you can write them in the chat, or you can just unmute yourself and ask directly. Maybe I will start with one question that I was curious. Like in the middle part of the talk, you were kind of using these tools to try to understand or predict how player will play their next move based on their ELO score. Yeah. I was wondering, you thought about trying to do different model depending on the ELO score also of the opponent? Like I was thinking I may actually do different things depending on whether I might know that my opponent is weak, then I know I can kind of trick him into something that will not work with other.
Yes, yeah, we've looked at this question quite a bit, because I was very intrigued by this idea that, like, right, there could be a number of things. Like I'm sort of strategically adapting to my ELO opponent. I might be subconsciously adapting, right? I might be intimidated by my opponent and not playing as well as I normally do, or and so we looked at this. We found very little indication, like in aggregate. This is clearly going on, but our sort of tools have so far not found it. But we keep looking for this because there clearly is something like this. One thing, actually, I should say, because I was talking about bucketing by ELO, one thing that we have a sort of new paper on arXiv about is creating personalized models of personalized Maya models. So basically, for players who've played at least, say, 1,000 games on Lichess, and there are, if you sort of go online every night and you play 2 or 3 games, then after a couple of years, you have 1,000 games. You can actually, that's enough data that we can fine tune the base Maya model. So I take your rating, I take the base architecture, and then I use fine tuning algorithms to create a personalized model, which can actually be as much as 10 percentage points better at predicting what your moves are. And so there becomes an interesting question of, like, this is now an even closer approximation to you personally. And, and then you can sort of ask, right, so you can ask about the differences between models of individuals. You can actually use the models for a kind of stylometry. It turns out from relatively few games, the model that best predicts the next move on these games is likely the model for that player. So it almost can be used in this inverse mode to figure out who is it, who's the author of these chess games, basically. We obviously would love to do this for sort of really, really powerful players, right? Wouldn't it be amazing to sort of create a bot that simulates famous players of the past, But part of the challenge is, as you see, the Maya performances start to drop off beyond about 2000. And it somehow has been hard to both match 2,700 rated human play, but somehow not just be playing like Leland, just winning chess. So one of the challenges that we're wrestling with is how to sort of have match players at extremely high ratings. Yeah.
Perfect. So I know that there's some question in the chat. I don't know if the person that wrote the question want to unmute, or I can just relay them otherwise.
Yeah, it's a good question. Yeah, so right, the phenomenon of prodigy, right? Because often there's sort of this proverb, right? That chess, math, and music are the 3 areas where you see prodigies on a regular basis. Right, such a thing as a prodigious, right? So do prodigies have a? Yeah, this is a good question. I'm curious. Feel free to say more about what you had in mind. I mean, I can say one thing that we've been looking at, which is, right, it is clear that there's a kind of representation that people have when they become good. I mean, obviously, it's called the Drosophila psychology because there's a gigantic amount of behavioral science research on chess. And there are these interesting analogies between chess and language learning, which you might not think should be there, right? That there's a hypothesis that some people make that, getting good at chess is more like getting good at a language than it is like getting good at, physical activity, like, tennis or baseball or something. And in that view of the world, like it helps certain things, that you acquire certain fluency when you do it at a young age. Because like one thing we've done in the Lichess data is I've been fascinated by this question of, like, can we look for signs of improvement? Like, here's someone who's literally played a couple of thousand games. And what's sort of striking is often for most people when they play a couple of thousand games in Lichess, they're not much better at the end than they are at the beginning. It feels like there's a kind of window where you get better, right? This kind of language learning window. And beyond that, it's actually hard to get better. So I think, yeah, there is this notion that there's a certain malleability in the representation early on. The prodigies sort of set that representation well. And that there's a lot of behavioral science research point to this, but it is interesting to ask whether in the machine learning framework, we could try to make use of some of those insights.
So let me, oh, sorry.
Go ahead. No, go ahead, yeah.
Can I ask a question or how do we do that? Sorry.
Sure. Feel free to ask.
Ozan, I think you were going.
Doesn't matter. Sure, I can go. I mean, I have one brief clarification question and a higher level question. So the clarification question is about the picture on this slide on the right. So I was thinking when you were presenting this prediction results, John, that the low skill individuals, their play would inherently have higher variance, and predicting their moves may be more difficult. And if I look at the top set of curves and just eyeball the peaks of these curves, it seems consistent with this type of behavior or prediction. But at the same time, I was thinking that given how variable the gameplay might be for low skill individuals, this 50% type of accuracy is too large, and I don't know how to interpret this. So do you have an interpretation of how we're able to predict so for low skill players?
Yeah, we have thought about that. It's a great question. And actually, I completely agree that like in my cartoon, it's probably not worth going all the way back to, but like this, like what would it mean to do well? Yeah, I think our conjecture was not this picture, but like a slope, because good players are presumably sort of more structured, more predictable. Yeah, so I think part of it, okay, so obviously there's always the possibility that like, yes, it's more variable, but that's actually a lower order effect than just somehow the inherent predictability of what they're doing. The positions are generally less complex for weaker players, but also I think it says there's a certain bedrock of just predictable position, as in there are a lot of things where you're faced with a fairly obvious threat and you respond in a fairly obvious way to it. And so that creates a giant additive term below everything. And so you can picture there's like this sort of additive bedrock of like, you should reasonably be able to predict this well. And then there's a steeper slope kind of, a kind of relatively steeper slope on top of that. But all of these are sort of, conjectures that, I mean, I think that's certainly a big part of it, right? That a certain non-trivial fraction of moves are just going to be predictable. I mean, not necessarily predictable by these engines that aren't trying to predict human behavior, but otherwise predictable. But yeah, this is a question that we've wondered about also.
Great. And the kind of the higher level question I have in mind is the following. Going back to the beginning of your talk, I completely agree that chess may be a good test bed for various decision making scenarios. At the same time, it is one setting where players have effectively identical representation of the decision problems they are facing. There's no randomness in decision making and so on and so forth. So taking what we learned from this talk or this setting and pushing it towards these richer settings where maybe individuals have different representations of the problem they are solving, where they have randomness in decision making, etc. How can we go from here to representing human behavior in those richer settings? Any thoughts on that?
Yeah, no, that's right. It's a very good question. So actually, one thing that I've been doing with some ongoing work with Senthil Mullainathan and with Annie Liang and Drew Freudenberg is on this, what we've been calling measuring the completeness of theories. And so what we've been doing is going into settings where there is stochasticity, for example, and where sort of the human can decide on the representation. So, essentially, for example, like, games played in the lab where the sort of optimal play is some kind of a mixed strategy. And ideally where players can sort of make choices about sort of how they even sort of think about strategy space. And then picking ones that are streamlined enough that we can actually write down the optimal behavior using table lookup, right? So we essentially try to create a table base for some of these lab settings. And then say like, how good are these table bases at predicting what human performance is? So I think, one thing that, and that was sort of an idea we kind of arrived at from the chess table base analysis that so this idea of looking for domains, where table lookup can actually be some kind of a counterpart to the analysis of the human behavior, I think is an intriguing, like, just to take a really simple example of this, there are more complicated ones. Work on human perception and generation of random sequences, right? So there are this genre of behavioral science tasks where I say, please write down a sequence of random digits, and I look at how you deviate from randomness. And we know humans have predictable deviations, such as the runs are too short, there tend to be too much of an equal number of zeros and ones, right? So the distribution is too peak near the middle. And so if you think about it, like suppose I said, okay, I'm going to ask someone to write down the first 7 numbers. I'm going to try to predict what they're going to put for the 8th one, which there are a number of studies like that. All of those studies are basically the study of a single empirical table of length 128, which is for every one of the 2 to the 7th possible bit strings, there is some human empirical frequency. And that's a fairly robust thing. You run repeated lab studies and you get about the same numbers. So there is a kind of 128 line table that's describing how humans behave on that task. And then you could ask the question, okay, now that I have that lookup table, I have various theories for quasi-random generation, right? So there's like a theory of Rabin-Vianos, there are other sort of theories. And so you could say, how does that do versus the lookup table? So that's sort of, again, a simple example of the kind of thing that we might want to do even with more complex settings, strategic settings, but things that have both stochasticity, representational issues as you're describing. And so I think if you can get it to be streamlined enough that there is a kind of lookup table involved, and that's sort of one angle we can try.
Mehmet, do you want to ask your question?
Yes, thank you. Thanks for this fascinating talk. It was really nice to listen to you. Embarrassing that I missed the beginning, so maybe you mentioned them, but I have 2 questions. So one is, does Maya give an evaluation of a given position, let's say the beginning of the game or any position in the middle game, based on the ELO ranking of the players? So that's my first question. Yep. And the second question is that, so obviously there is no human player above 2900 ELO, right? So is it possible to actually predict, given the data that you have for lower ranked players, predict something in terms of their error rates? What would 2900 human player look like?
Yeah.
What would their decisions look like? Is it something like this possible?
Yeah. Okay. Yeah. Those are both good questions. So on the first one, yeah. So as a technical point, to get optimum performance from Maya, so those of you who sort of work with like neural net training know that like if you add heads to a neural net, even if they're heads to predict something that's not your objective function, you can do better, because you're essentially forcing it to develop internal representations that are going to help it overall. And we actually find that with Maya, that having a head that tries to predict the probability that a player of rating X is going to win from this position does improve performance and move prediction. So yeah, so it is useful to actually have a head that's predicting human win probability, even though winning the game is not actually Maya's objective function. And that's sort of something that's sort of familiar from a lot of neural net training, where having a multi-headed training can be useful. For the second one, yeah, this is a question that fascinates us, which is, we could potentially use this. I mean, our challenge, of course, is you see all these curves start going down. Like, it gets harder and harder to train Mayas as the rating gets higher. And so but if we could break through that impasse, a fascinating question is like, could there be a thing that could human play reach 3,000, right? Could human play reach 3,100? Like, is there some maximum limit on you? Because it does feel like, engines have reached 3,300, 3,600, depending. It's hard to measure ratings up that high, but they're in the mid 3,000s. And when you look at their games, some of their moves are just profoundly incomprehensible. But the question is that necessary? You can imagine like Maya 3,300, which is like, it's like humans. It's just a little bit better in every position, right? It just keeps, right? Because you almost feel like if you could just take human play and just kind of raise the temperature a little bit, and just make every move just a little bit better, you'd have a 3,300 rated player who didn't play incomprehensibly. They just played really, really well. Or maybe there's something inherent that says that's not possible, that to get beyond 3,000, you're just going to have to make moves that are just not comprehensible to us. And so, yeah, we've actually been quite fascinated by that question. We don't have a great way to approach it. We feel like if we could train Mayas up to much higher ratings, we would at least start having a way of thinking about that. But that's sort of the step that we're trying to work on right now. Yeah, but yeah, thanks.
Oh, hi, John. Thanks. I have one question. So for your example of Carlsen, it had things like win in 16 moves, win in 20.
Yeah.
So obviously, in those cases, you'd probably become apparent that it's a win after 3 moves if you've made the right move. So my question is, can you say anything in the examples with sort of high blunder potential about the game tree at that point? It sounds like you've been looking at, you know, what fraction of the moves are good and bad, but can you say something about the structure of situations that have high blunder potential? And if you can, does that tell you anything about how people are actually thinking?
Yeah. So this has been one of our sources of frustration. We've had many sources of frustration, and like the things that we wish we could discover in here. And one of our sources of frustration is that the shape of the game tree has given us less signal than we would have liked. I mean, implicitly, Maya is using the shape of the game tree. So if you aim a neural net at it, then something comes out. But for us trying to get insight, we had this sort of early insight, which is that this, you know, if your blunder requires a difficult move for the player to capitalize on, right? So like if after your blunder, the correct move has high blunder potential, then it's sort of harder for you to realize it's a blunder. And you do see that effect. So that's like a depth one issue in the game tree. But yeah, we've definitely been very curious about like other things about the shape of the game tree somehow recursively ought to matter. Yeah, and as you're mentioning in the chat, you know, right, you might be able to get some effective measure how deep people are looking. It's been hard to find that. I will say that the numbers in table bases, win in 16 moves, are a bit illusory, because like a strong chess player, of course, is going to think, I am 3 moves away from promoting the pawn, and now it's going to be king and queen against king. I know I can win king and queen against king. I don't know how many moves it'll take. It'll take like 12 moves or something, right? Because I have to like chase the king to the corner and not stalemate them and administer checkmate. But that's like a subroutine call for them. They know that's going to work. So they're really thinking about, how do I get the pawn to the queen square? And so they think of it as it's a forced win in 3, and it's very easy for them. The tail base says white wins in 15. You're like, wow, they saw 15 moves ahead, but they didn't. They saw the 3 moves ahead to when it became just sort of rote. And so that sense in which the numbers in the tail base turned out not to be that useful for the thinking. And it is much more about these sort of local phenomena, as you're saying, like the next few levels of the game tree. And that's where we have like this depth 1 insight seems to hold up, but a lot of other things feel like they're surely there, and we so far haven't found them.
And I think there is a related question to this in the chat that says, is there a way to use the plot of depth versus performance to try to capture how many moves a player of a certain elo looks ahead?
Yeah, I think here, I guess I would say, I think the answer is no, because I think the model of human, of sort of highly proficient human play is just too far from look ahead. And in some sense, like the failure of Stockfish at greater depths to really match things, you know, the fact that sort of at all high depths it's not doing a great job matching, and the fact that actually it's non-monotone, I think all of that points to human decisions are not well approximated by minimax search up to a certain depth. And in some sense, the fact that you can improve so much on Stockfish at matching humans is sort of some indication of that. And again, back to chess as the Drosophila of psychology, there's a lot of behavioral psychology research. I mean, one of the famous psychology results in chess is sort of talk aloud protocols on choosing chess moves, and the kind of stylized fact to emerge from that, which has been reproduced a number of times, and is sort of actually a useful metaphor that gets ported to other domains also, is that in a talk aloud protocol, as the player's rating goes up, they talk about considering more and more moves, more and more options as they go, and more variations. And then there's an internal maximum, and as the rating keeps going up, the amount they overtly talk about goes down. Because in some sense, it's all been like sublimated into unconscious processes where they don't even consciously know why they're pruning knight to f5. They just know it's a bad move, and they're focusing on, you know, rook to h1, and they're not explaining it to you in terms of variations. They're just pruning it before they're even reaching the point of consciously talking about it. And that's sort of a famous result in the psychology of chess. And I think it does say something about the way in which minimax search is somehow not a great model for sort of the highest levels of human chess play.
Okay, perfect. So I guess if there's no more pressing question, we can thank our speaker again. This was an amazing talk, and thank you so much for staying and answering all our questions.
Sure, thanks very much. Thanks for all the interesting questions. Appreciate it.
Perfect.